Hello, everyone. Welcome to the plenary session with the second keynote speech that will be held by Jack Wist, followed by the IEEE ITSS awards in about an hour from now. Jack, are you here? Yes, you are.
Yes, I'm here. Good morning. Good afternoon.
Hi. You can take over the screen sharing.
All right. I will share my screen. Oh, it says I cannot share my screen while another participant is sharing.
Okay, then I will stop doing that on my side. Okay.
All right.
The presentation is titled Metrics, Methods, and Assumptions, the state-of-the-art of AV safety assurance. And perhaps I could say a few words about our invited speaker. Jack Wist is a senior principal engineer at Intel and VP Autonomous Vehicle Standards at Mobileye. In his nearly 20 years of career at Intel, Jack has built a reputation as a change agent in new industries with significant technical contributions to a wide range of industry-first products and standards in complex, heterogeneous, high-performance compute solutions in markets that are embracing high-performance computing for the first time. With end-to-end systems perspective, Jack combines a unique blend of embedded product experience with a knack for elegant software and systems design that will accelerate the adoption of autonomous driving. Jack is also the co-author of UPnP Design by Example. He's an adjunct professor at Portland State University. And I don't know how, but he managed to be a holder of 40 patents with dozens pending. Congratulations. We look forward to your presentation.
All right, can you hear me, everyone? I seem to have some connection troubles.
Yeah, we can.
Are you able to hear me?
Yes.
Okay, very good. Seem to be having some connection troubles, but hopefully that will not cause more problems. But thank you, everyone. I appreciate the opportunity to speak with you today. Today, I'm going to talk about metrics, methods, and assumptions. And in the context, also provide an update about what we will call the state of AV safety assurance. And so first, let me pose a question and ask, what will our future look like? Will the introduction of autonomous vehicles be clean? The introduction of original automobiles into the world was quite messy because the roads at that time were owned by horses, horse-drawn carriages, bicyclists, people. So it was a very chaotic introduction. And so it makes us think then, what will the introduction of automated vehicles look like? Will it be similarly disruptive and chaotic? Or will we have a glorious future with the seamless integration of automated vehicles? But we have some challenges. So for example, what if every automated vehicle on the road had a different definition of what it meant to drive safely? What if every state or country had a different definition of what it meant to drive safely? And so with these challenges, or what if every time there was an accident, it required lawsuits to figure out who was driving safely? So in this sense, we have a challenge, because if we don't answer these questions, we are going to have a chaotic introduction of automated vehicles. And so really the point is, as an industry and with the government and with people, we must come to agreement on what it means for an automated vehicle to drive safely. Because if we don't, there will be no AVs. So let's take a look at a case study. What happens when safety is common ground? The automotive industry has spent a century competing on safety, but aerospace works differently. So just by example, in 1997, the Federal Aviation Administration created a new commercial aviation safety team. And the point was not just to look at accidents that had already happened. The point was to proactively identify and mitigate new risks that had not happened yet. And amazingly, the result of this was a over 83% reduction in the fatality risk from the creation of that team. And then overall, the commercial aviation fatalities in the US alone have decreased by 95%. And so you see the statistic down there on the left. The difference between the fatality rate per billion kilometers traveled by plane versus car is striking. And one of the biggest contributors to that is that the FAA created this commercial aviation safety team to proactively, in advance, identify, define, and mitigate risk, not just looking at it after the fact. And so it's worth considering, you know, when the FAA offers these constructive, collaborative, non-punitive ways for industry to work together to define and assess risk before it happens, isn't this a model that we would be wise to adopt in the automotive industry? Think about this differently. Today in the US, 38,800 people died in 2019, lost their lives due to auto accidents. And so if that were front page news in the newspaper, every day of the year, the newspaper should have a headline that says 100 humans die by car, every day of the year in the US alone. So what if instead we were able to reduce that by 100 times to 388? That would be the single greatest achievement or reduction in safety for the automotive industry. It would be a remarkable reduction that would save tens of thousands of lives in the US and millions of lives across the world. But what that means is we would still have the front page of a newspaper say, AV or robot kills human every day. And now just even one accident, without even potentially a fatality, every time there's a fender bender, it's almost front page news when it involves an automated vehicle. So we should ask ourselves, which of these futures is more desirable? Should we accept 38,000 people per year dying in the US? Or should we realize that we have an opportunity to do something more? But the point is, absolute safety is not possible. We will never get to zero. And so what we must ask ourselves is, when crashes happen, whether it's 0 or it's 1 or it's 388, if that is the level, we have to ask, is that okay? And we either need to accept the benefits of automated vehicles versus the risks. In other words, accept 388 instead of 38,000. Or we need to revise our definition of what it means to drive safely when accidents happen. And so here is the unique opportunity that we have. We have, with this technology, for the first time, to proactively set the level of safety we desire. I'm proposing a level of safety of 100x improvement would be fantastic, but that's not for me to decide ultimately. That is for the public. That is for governments to decide together with industry. And so we need to ask ourselves, is that enough? Is that safe enough? But the point is we can ask this question, we should ask this question, and we have the ability, technically, to achieve whatever desired balance between safety and risk that we desire. And so one of the useful tools to contribute to this is called responsibility sensitive safety. This was a safety model that was released in 2017 by Intel and Mobileye, and it is an open and transparent technology neutral model for autonomous driving. It is parameterized, so it is flexible. You can plug in different values to the parameters to represent different cultural definitions of what it means to drive safely. Driving safely in China is very different than driving safely in US. Driving safely in Italy is very different than driving safely in Switzerland. And so driving safely is cultural. So we must adjust our definitions to what the people of the countries in which these vehicles will be operating find acceptable. And so it is a useful tool, RSS, and really provides a framework for regulators and researchers to understand what is that acceptable balance between safety and usefulness. What is the right number that we should be shooting for? So just to remind everyone, if you don't remember, RSS defines some very basic common sense behaviors for driving safely. For anyone who has taken a driver's test, these should look very familiar to us. When we take a driver's test, the examiner is certainly looking to make sure that we are following the speed limit, that we are stopping at stop signs, we are obeying traffic signals. But really what they're looking for are these characteristics, because these general foundational behavioral characteristics is really what it means to drive safely in the region where we live, and are the fundamental tools that allow us to navigate within traffic with other human drivers, pedestrians, bicyclists, and the like. And so what RSS has done is formalize these rules into mathematical equations that are parameterized that we can then plug in specific values. So we'll take a look at an example later. So I am happy to announce today that very soon, we had hoped by this moment, actually right now, we will be launching a brand new research center to support all of the researchers around the world that have taken this model and done fantastic things with it. We plan to feature the many dozen papers that have already been published and provide a discussion forum for researchers to engage with myself and our entire research team at Intel and Mobileye if you'd like to discuss more about RSS, and if you have an interesting research idea you'd like to share with the community. So we have an official landing page down there at the bottom. So stay tuned. Very shortly, we will have this research center launched, which will provide really a new level of transparency and collaboration with an industry partner on AV safety. So we look forward to seeing many of you there. So let's go back to this question though, about an autonomous vehicle versus human drivers. Because we are different. So let's think about how would a human driver determine a safe distance? A human driver uses tricks. So we have these things called like the 2-second rule. And that's where the car that you're following, you're supposed to look at a marker on the side of the road, and then you're supposed to count 2 seconds to see when you cross that marker. And if you count to 2 or 3, whatever the number is, you have successfully achieved a safe following distance so far as humans are concerned. But I think many of us understand that that's a very simple metric. It doesn't account for a lot of other factors. And so with automated vehicles, we have a better way. We don't have to guess. So here's an example of the safe distance formula for RSS's rule number 1, how to maintain a safe following distance. And so we have an equation that's parameterized, and this is basically just physics. We have objects of mass in motion here. So we have the velocity of each of the vehicles, we have braking capabilities, we have reaction time, we have the amount of acceleration that could be happening during the reaction time. You can also add to this things like coefficient of friction, the condition of the brakes. There's a lot of different things that you could add to this that would really help to precisely a safe distance be. And so this is what we can do with an automated vehicle then. So there's an important trick to this though. Not all parameters can be measured or known. Certainly the velocity, position of other vehicles can be measured. We can know our own braking capability. The automated vehicle can know its own reaction time. But what about the braking capability of the vehicle that I'm following? Beta max is that parameter. This is a parameter that represents an assumption about what is reasonable and foreseeable for the vehicle that I'm following. What should I expect the braking capability is of the vehicle that I'm following? Because depending upon what the value of that parameter is, my following distance could be radically different. So let's take a look. What should this value be? If you look at a variety of different vehicles on the road, braking capability varies quite significantly. A 2015 Ford F-150, 8.19 meters per second squared. But a 2018 Porsche 911, 12.5 meters per second squared. NHTSA did research, and they found that human drivers typically brake with a force of around 6.5 meters per second squared. So what should we assume? Should we assume the worst possible case all the time, the theoretical maximum case of any vehicle on the road? If we do, that would certainly provide a strong guarantee that we're not likely to rear end the vehicle that we are following. But what if the technical maximum is 15, 20, 30 meters per second because someone has taken a race car and put it onto the road, and someday, somewhere, that automated vehicle could encounter that car? So if the requirement is you should never crash into a vehicle that you're following, that's what we'd have to set the value at. And now the automated vehicle is maintaining extremely long following distances, and we have a vehicle that is very annoying on the road, that nobody would like on the road, and certainly society would not accept this technology. So the question then, again, is what should the value be? And I think this raises a very, very important point. We need to consider the difference between parameters and their values. The role of industry through consensus-based standards is to define the parameters of how the technology operates, because those parameters is how we can adjust the performance of the vehicle. The role of government is to pick values. And there's many examples of this already. For example, the speed limit is a parameter. Its value varies on road. So when a new road is built, what is the first thing that the government does? Is they pick a value. They pick what should the speed limit be. And that value is a trade-off between safety and usefulness. If we wanted to guarantee there would never be any fatal accidents on a new road, we could set the maximum speed limit to, say, 10 kilometers per hour. There might be crashes still, but not likely to be fatalities. But we don't do that, right? Because we want roads that have utility, that have usefulness. And so we set the speed limit to be 60, 70, 80 kilometers per hour instead. So that's picking a value for a parameter that's a trade-off between safety and usefulness. In other words, it's setting the acceptable risk balance. We can think of other things. There is a new regulation about what are the minimum sound requirements for electric vehicles, right? So they don't creep up on you and accidentally hit you. If you're a pedestrian, you can hear the car coming. And through lots of debate and negotiation between industry and government, at least in the United States, that value is 62 decibels. Is the minimum sound requirement that an electric vehicle is going to be required to make so that pedestrians can hear it. Why 62, right? Why not 70? Why not 100? A lot more people would hear it, so more pedestrians would probably step out of the way, especially if they have earbuds in, right? But again, it's about picking a number. It's about what's an acceptable risk balance. And so we assert that the role of government is to pick these values for automated vehicles as well, to understand what is the right value, how safe is safe enough, and what is the balance then between the usefulness of this technology, but also the utility of it and safety of it as well. So we have values all over the place. We have values for maximum braking. We could have values for what should I assume the maximum acceleration is for an occluded pedestrian and more. But our role as industry is to bring frameworks like RSS to standardize things like assumptions, which we'll talk about, and we look forward to engaging with government to help us pick what are the right values for the geography in which we deploy. So let's take a closer look then about the role of assumptions in safety models. Assumptions are represented by parameters. And so we talked about this first assumption, this assumption about what is the maximum braking capability of the vehicle that I'm following. That's a guess, right? I can't know it precisely. And so I'm making a guess. And so here we see then we could define that. We can define the maximum longitudinal deceleration as a value. Let's take a more complex scenario with a pedestrian. Here we have a scenario where a pedestrian is on the road. That happens sometimes, right? Here the sidewalk is closed off. You can see the construction cones. We might be in an urban environment, and on many urban streets you do see pedestrians walk around. So for pedestrians, we have a number of other assumptions we should make. What should I assume their maximum longitudinal velocity is? What should I assume the maximum longitudinal acceleration is? What about the heading rate, the heading angle rate change? These are things that I need to know before my car starts to navigate next to that pedestrian. Now, there are theoretical maximums. We could look at Usain Bolt, the fastest human on the planet, perhaps, and use the values for him. But are those values reasonable? Are those typical? Would we really expect that in most cases? And the question is, if we used such extreme values for the fastest human on the planet, how does the AV able to navigate in areas where there are lots of pedestrians? But at the end of the day, these are assumptions, right? We can't read this person's mind. This person can't communicate these values to us via V2X or anything like that. We just need to make a guess. But we need to make a guess that is responsible, but also reasonable and foreseeable. And so at the end of the day, driving safely is about using the societally acceptable values and proving that you are doing so. So we get to this question then about how should government regulators pick these values? We're doing this work, we're standardizing these things, which I'll talk about in a moment, but how should we pick the value? Do we just pick them out of thin air? Or should there be a methodology to pick these values? And so let me take a look at an example here. Let's look at a case study. Here's an example of an excellent research paper published by some colleagues from Tongji University that was published as part of the Transportation Research Board annual meeting just earlier this year. And what they did is they looked at naturalistic driving data and tried to calibrate the values based on that data. And so here we have a large study for naturalistic driving data from Shanghai, over 20,000 trips over a 3-year period. And so an incredibly rich data set of human drivers and human pedestrians, human bicyclists, motorcyclists, etc. So they looked at that, and then what they did is they identified 219 safety critical events. So these were events where you had to have extreme longitudinal deceleration or lateral motion to evade an accident. So in other words, in NHTSA language, we would say this is a pre-crash scenario based on that study. But this is based on Shanghai driving. So 219 were the number of safety critical events. Then what was done is then parameter values using the RSS safety model were identified to understand what are the values that I need to plug into the safety model in order to provide complete coverage for these 219 safety critical events. And through some use of genetic algorithms to make sure that we aren't being overly conservative, we identified a set of values based on that naturalistic driving data set. And so you can see there, looking at the beta max value, 6.1 meters per second squared was derived as an appropriate, reasonable, and foreseeable assumption about the maximum braking capability of other human drivers on the road. That sounds pretty reasonable, right? And it's consistent with the NHTSA study, which found a very similar value. But as I said, that's only half of the theoretical braking capability of vehicles that could be on the road. So quite interesting difference. So with then these values, then we can take these values, plug these back into simulators or real cars on the road and understand, okay, how would these values perform then? Do I still have a naturalistic driving vehicle using these values? And what the research study found is that not only did you still have a naturalistic driving vehicle using these values, but it was able to identify these safety critical events on average of almost a second ahead of a human driver. And we reduced the time integrated TTC of 94% of the events. So a really interesting methodology from start to finish, starting with naturalistic driving data, identifying safety events, deriving parameters, and then testing those parameters back again to see how we did. So I'm not saying this is the only methodology, but this is a wonderful example of something that we could do as industry and as research and as the research community to help governments figure out what should those values be. So in summary, I think this example shows that RSS is a useful an open and transparent framework that will help regulators be able to define what is the acceptable risk balance by setting values for things that cannot be known or measured. So what has the industry been doing though overall? Let's take a look at the state of the automated vehicle industry. Quite a lot has happened. Here's a timeline from 2017, starting with when we released the first version of the RSS paper. We remember in 2018, we had the very first AV safety workshop at the ITSC conference, and here we are today. Just yesterday, Sunday, we had the third safety workshop that we were honored to host. We had other important events like the formation of the Institute for Automated Mobility in the US in partnership with the state of Arizona. NIST held some workshops, the Safety First for Automated Driving white paper, and you start to see more and more and more things kind of happening. Things are really picking up. Industry is really doing a lot of things to try to collaborate and build consensus-based standards. We had the OL4600 standard published. We had the AV test initiative, which was established by NHTSA in the US. And hopefully, we will have the first version of IEEE 2846 sometime in 2021, but we'll talk more about that standard in a moment. So there's a lot of activity, but you're seeing it's very kind of focused, right, in the latter part of the recent year. And so why is this? And really, industry has come a long way in just 12 months. There's been a significant shift from 1 year ago where the best way to describe it would be reluctance. There was a reluctance to collaborate on a pre-competitive safety work. Typically in the automotive industry, you standardize safety after a technology has been deployed, not before. And so this is a significant mindset change. You had players that were not participating or collaborating, you know, because maybe they were worried about losing a perceived leadership position. You had debates about which standard development organization is the right place for this collaboration. And you had even a war of words, even in the press, between the role of different standards from different standards development organizations. But today, things are much improved. We're collaborating much more than we're competing, particularly when it comes to AV safety. We finally moved past these old metrics like miles driven, knowing that metrics will still be needed for sure, but we need better metrics that tell us more about the overall performance and safety of the vehicle. We have more players, more industry leaders are getting involved in standards, and we have new important standards efforts like IEEE 2846 and the ISO 4804 work, which are really coalescing all the major players together into some foundational standards for the future of the industry. And so one thing that's common though, that I think is key here, is to remember that transparency in safety assurance is key. As the aviation industry has proven, when you're transparent and you openly talk about safety and you think about risk and you think about the things that could happen in advance of them happening, together as an industry, we can create a better future. And so really, we believe strongly that safety is something that should be common ground and not a point of proprietary differentiation. So let's take a look at what's happening from a standard standpoint. I've built something here called the Hive of activity, so excuse the bad pun, but there's a lot of work happening. We are busy as a bee working around on these standards. So what kinds of standards do we need though? And so this is interesting to think about, right? Because there's not going to be one standard that rules them all. We're going to need a collection of different standards. And so first we should think about, how do you define, develop, or test the vehicle? And so these are systematic process standards like ISO 26262 or the forthcoming SODIF. They don't tell you what to build, but they provide a methodology for how you should build something to hope to make sure as much as possible that what you are building is going to be safe at the end of the day. Then you should think about, okay, should the design of what you be built? And this is where we have safe by design architecture standards like the aforementioned ISO 4804, as well as the in-progress SAE J3131 reference architectures and interfaces document. So these provide high-level definitions of what a safe by design architecture of an automated vehicle should be. Then, okay, so I've built something. Why do I think it's safe? Well, let me file a safety assessment report that conforms with the UL 4600 standard, or the voluntary safety self-assessment reports from the Department of Transportation in the US. This is documenting why I think the way I built my vehicle is the right way. The way I made this choice versus that choice is the right way, and here's my evidences of how I've tested it, for example, internally. But then we should think about, particularly from a regulatory standpoint, okay, so I've built something, what should I test? What scenarios? So here we have work also in ISO, as well as the Pegasus project contributed a large number of scenarios. So this provides us then a database of scenarios that we can use. Then we should consider, okay, I've performed within a scenario. Did I pass? Did I fail? Was I successful? What does that even mean? Well, here's where we need metrics. And so here we have metrics. There's a metrics paper that was produced recently by the Institute for Automated Mobility, as well as a new SAE project that's going to be starting very soon, J3237, that will be looking at performance metrics for an automated vehicle, where you could use those metrics inside a scenario. But then, oh, how did you test it? Was it in the real world? Was it in simulation? Was it on a test track? We need standards for test methodologies. And this is where we have work from the UN, the Validation Methods for Automated Driving, as well as, for example, the University of Michigan, which published a set of papers called the ABC testing methodology. So you do all of this together, but then we're still missing kind of one last piece. What is a societally acceptable driver? What vehicle should get a driver's license, and is it going to drive in the way that we want it to? And so ultimately, this is where we need help. This is where we need help to understand what it means then to drive safely. And this, as I'll talk about shortly, is the IEEE 2846 standard. So if you look at all of this, though, let's reflect on this. Safety assurance is not just one standard. It's a framework. And if you follow all these standards, what you're going to do, the standards on the outside, you follow good process standards, you follow the safe by design, you filed a safety assessment report, you tested scenarios using metrics in simulation and on the real world. And so what you've done is you've responsibly built an automated vehicle. You took care in what you did, but you've not necessarily built one that achieves acceptable risk. Because acceptable risk, as we just defined, is based on the values that are used for these parameters that represent assumptions about the behavior of others. And it's only IEEE 2846 that provides such a framework for acceptable risk. So let's talk about this wonderful standard that I humbly am honored to be chairing. So IEEE 2846 is a standard called Assumptions for Models in Safety-Related AV Behavior. We have a fantastic set of collaborators representing OEMs, mobility as a service providers, tier ones, governments, universities. We have a liaison agreement with ISO and are developing one in progress with both SAE and ITU. So we have an incredible set of people that are participating here, and I'm honored to be co-chairing this with my colleagues from Waymo, as well as our secretary from Uber. So we have a fantastic set of participants in this group, and that example that I gave earlier about the two scenarios with car following and a pedestrian and the assumptions that are needed in those scenarios actually came from the work that this group has been doing. And so we are happy to be doing this work in partnership with the IEEE. So let's think then about the role of models and metrics. And so if you have an outcome-based metric, you might have just gotten lucky. So in other words, take me to the airport and I'll give you the driver's license. Okay, well, great. I got there successfully. How do you know you didn't just get lucky, right? So, and the point is only metrics that are based on models can differentiate between a lucky outcome and the automated vehicle passing a test for the right reason and being confident that it's not going to be able to drive safely, not just in that one lucky scenario, but in lots of scenarios that it's going to be exposed to. So we were pleased to work with the Institute for Automated Mobility, which is a research institute in the state of Arizona, on a proposed set of metrics for ADS-equipped vehicles, in other words, automated vehicles. This is the first set of metrics that are based on safety models, and we are now evaluating these metrics. They're being tested on roads. Intersections are being instrumented. We're monitoring cars and traffic going through that intersection, and we're evaluating these metrics to see about their usefulness. Are these the right metrics to be using for the performance assessment of automated vehicles? So what are these metrics, you might ask? Here's a table of them. They have different categories. We have minimum safe distance related metrics, kind of similar to what we talked about already. We have some universal metrics like a collision. A crash is a crash, so just count that. Same with the rules of the road. We also have some gray box testing. And what we mean by gray box testing is we might need some limited information from inside the automated vehicle, perhaps from its data recorder as part of a test. And then we also preserve some traditional traffic engineering related metrics just to see, are these still useful? Things like time to collision or modified time to collision. These metrics have been used for decades to analyze and understand human drivers. So the question is, what worth do these have for automated vehicles? So hold that thought, we'll speak more on that in a moment. So let's take a look at what one of these metrics might look like. So here's a metric like a following distance, so minimum safe distance violation. So this is a violation where if this metric is positive, what it means is your vehicle itself initiated or originated the unsafe following distance. Because if the vehicle in front of you were to brake and now you have an unsafe following distance, that's not necessarily, you didn't cause that to happen. The vehicle in front of you did. But what this says is that during the normal course of operation, if you're maintaining a minimum safe distance, the metric records 0, meaning it's negative. So if it's positive, that means that you've done something. You've accelerated into that vehicle that you're following. But what should you do then if that vehicle that you're following would decelerate? So now we have a different metric here, which says that, okay, if that person that you're following were to decelerate, the automated vehicle itself should decelerate as well. So in other words, it should perform a proper response. And so in this way, what we've done is we've created metrics out of the safety model. And remember, the safety model is what uses the values and the assumptions. And so in that sense, what we've done is we've created an ability to assess the performance of an automated vehicle and whether it is using the acceptable values to society and government for its performance and its behavior. So speaking of government, let's look briefly before we finish up about what are the latest government developments. Well, here we've had some very exciting news actually. Very recently, the UNECE released what really is the most advanced regulation on automated vehicle functions to date. It is the world's first regulation, in fact, covering automated lane keeping use cases, which is really a level 3 kind of use case for automated vehicles. And so it's that the automated driving system shall not cause collisions that are reasonably foreseeable and preventable. Remember those words, right? Reasonably foreseeable and preventable. Because what does that really mean? What's reasonable to expect and what's reasonable to prevent? Again, which means assumptions, right? What can I assume about the braking capability, for example? And it also says that if a collision can be safely avoided without causing another one, you should do so. So it should sound pretty familiar, right? Because those are very similar to those common sense behavioral characteristics that the RSS model defines. And so this regulation defines 3 specific scenarios that are critical for safety. It defines a cut-in, it defines a cut-out, and it defines a typical deceleration. But you'll notice in each of those pictures, it's kind of maybe a little bit difficult to see. I'll move with my mouse if you can see my mouse. But there is a metric basically that they're using in this regulation to define what is a safe distance. And what it is it's a time headway of 2 seconds. So quite amazing here then that basically the most advanced AV regulation in the world is still using the 2-second rule. And as we've already proven, we can and we must do better for automated vehicles. So how does this regulation stack up using an actual automated vehicle safety model? We did an analysis with RSS on this regulation, and we found that the use of a formal safety model definitely provides a much more accurate way to measure safety in these regulation required scenarios. So not only can an AV with RSS fully comply with this regulation, but what we found is something very interesting. We found that if you precisely calculate the following distance, in some cases, it's actually okay to follow closer than 2 seconds. But worse, in some cases, in fact, many cases, 2 seconds might not be enough. And you might think about a scenario where there's standing water on the road, for example, or you're going at a very high speed, or you change the value of the assumption of the vehicle that I'm following. And you say, instead of 6 meters per second squared, I'm gonna assume that vehicle can brake at 12 meters per second squared. Well, in that case, 2 seconds is not enough. And so again, we need to think more carefully in the development of regulation and make sure that we don't persist these human-oriented metrics, and that we are doing better, and that we are precisely calculating what safe distance should be. And safety models and standards like IEEE 2846 are an excellent way for us to do that in future regulations. So in summary, here is my call to action. So for industry, what should we do? We should continue working with government and align on what it means to drive safely. This is essential for us to ensure that we have a positive and welcoming introduction of this technology into the world, instead of a chaotic introduction like the original automobiles enjoyed a century ago. Second, we need to continue driving industry standards forward on these consensus-driven standards like IEEE 2846 and ISO 4804. But finally, what about the research community? The research community should focus on deriving new and novel methods to help industry and government together derive what are acceptable risk values that are used as parameters in safety models. Because ultimately, it's those numbers that define that balance between safety and usefulness, and are going to define how safe is safe enough for a country or a region so that we can deploy automated vehicles, and do, for the first time ever in history, define that balance in advance of deployment, not afterwards. So thank you very much for your time. It's an honor to be here. I wish we were all in Greece together, as I'm sure you all do as well. And so I look forward to your questions.
Thank you very much, Zach. We have some time for questions to Zach, so you can unmute your microphone and go ahead with questions if you want.
I apologize, everyone. I seem to be having some connectivity trouble. I didn't hear if there was a question there.
No, there wasn't.
Okay, sorry. I thought it was maybe just me. I've turned off my video in case that was contributing to the bandwidth troubles.
Okay. Then it appears there are no questions. Zach, thank you very much for the
chat.
Professor.
There were questions in the chat.
Okay. Professor Ioannou and Professor Papageorgiou.
There were some questions in the chat.
Yes, I see that as well. Professor Ioannou, then first, please unmute yourself and
yes.
go on. Yeah.
Good afternoon, everyone. Very interesting talk. This is definitely a serious, safety is a very serious issue in the deployment of automated vehicles. The question I want to ask is that I take the extreme case of a truck that has very limited braking capabilities, and truck drivers know that, and they keep a much bigger distance from other vehicles than passenger vehicles. Now, how would an automated vehicle handle that in this situation? Say, in this case, a driver will know that you shouldn't cut in front of a truck, even at a 2-second distance. But what if the automated vehicle do it, and when you compare the two, you come to the conclusion that if it was driven by a human, the accident could have been avoided. But because of the design, we have an accident. How do we put all these things into standards? I think that would be a very difficult issue.
Yeah, thank you. It's a very good question. So I think it actually goes back to those assumptions, because as part of the safety model, for example, that we've introduced, in addition to a maximum braking, there's also sort of a minimum braking value as well. And so if you're performing a cut-in, you can know what are the braking capabilities of that vehicle. And if it's a truck and you know it has very poor braking capabilities, you can calculate essentially the reverse equation.
I know that you can calculate. The problem is that you don't know that it's a truck. That's a problem. I mean, if you know, obviously, there are many calculations done with all kind of configurations that show you. But the problem is that because the vehicles are not connected, then the automated, unless the automated vehicle can identify who is who and distinguish between a truck and a Porsche, then it will not know how to calculate. So it has to assume some conservative. If it assumes that every truck, every vehicle I cut in front is a truck, then you get a very conservative spacing. So
correct. Yeah, I understand your question now. So the values for these parameters definitely can vary based on object type. And so automated vehicles, as they do their object identification and classification, do typically know the difference between a truck and a vehicle, just like we know the difference between a pedestrian and a bicyclist, because they have different behavior. They have different.
But then that has to go to the standards also, right?
Correct. Yeah. So
how able is a vehicle to identify the classes, the vehicle classes? So that becomes part of the equation. Otherwise, yeah.
Yeah, correct. And so I think one of the things that I didn't touch upon today in terms of the testing methodology and metrics is, what are the metrics and testing methodologies for perception, for sensing, right? My talk today was purely around the decision-making part, but you're absolutely correct. We do need standards to understand what should the vision test be, essentially, for an automated vehicle, and what should we be confident it has the ability to see. So for example, as you say, the difference between a truck and a car. And so we do need new standards in that area for sure. And I apologize, just didn't talk about that in my talk here today.
Okay, thank you.
Let's see, it looks like there was a question in the chat that I'd be happy to take. A question about security. Yeah, a very, very good question, because obviously the security of an automated vehicle could definitely lead to serious safety considerations. And so I would point to the ISO 4804 document, which is a safe by design architecture for automated vehicles that includes cybersecurity. And it does define fallback and failover capabilities that could be used in a variety of situations, up to and including potentially an identified malicious attack that would allow the vehicle to transition to a minimal risk condition and a minimal state for a variety of failure scenarios, potentially including cybersecurity as well. So that's in the safe by design architectures is where that's being considered.
Can I ask a question?
Yes.
Yes. I have two questions that are coupled. The first one is that you talked in examples mostly about car following safety problems. Is your feeling that car following is more important in terms of safety, more challenging than lane changing, or the other way around, or both are equally challenging? And the second question that you may find weird, but I have my reasons to ask, is what would be your spontaneous answer in terms of safety if in a population of automated vehicles only, there would be no lane structure on the road. The vehicles would float on the road without the need to apply lane discipline, without lanes, it says.
Okay, yeah, very good question. So for the first, no, there are many scenarios that are important. I use lane following just as a simple example, but I can say, for example, in the IEEE 2846 work group, we are looking at not only lane following scenarios, but we're also looking at occlusion scenarios. We'll look at intersections, you know, any geometry of road or road type and action, including cut-ins, cut-outs. All of these scenarios are definitely relevant, and we need to be thinking about the assumptions for all of them. And so I just provided that one example just as a simple example for the talk today, but you're absolutely correct. With regards to the second question, yeah, it's quite interesting actually. The safety model that we released, RSS, actually does support, say, a mode of operation where the environment is completely unstructured, where there's no concept of a lane, there's no concept of priority, there's no concept of anything like that. It's just a big, open, empty space, essentially, where you could have a mix of cars, pedestrians, bicyclists, anything, and it proposes a model for how to deal with that, because those are common environments that we still see. Parking lots, for example, or you're going to that summer music festival and you park your car in a big grass field. You know, these kinds of things are going to be someday real world scenarios where automated vehicles are going to need to operate. And we do provide a method for how to deal with that that's based on angle of motion, rates of heading change, where you can then basically define a region for where the vehicle would be, but also knowing its braking capability, the region by which it could avoid based on the actions of others. So I would refer you to that paper, a quite interesting section of that original RSS paper that talked about exactly those kinds of situations.
Thank you.
Thank you for the question.
Jack, there are a couple of questions in the chat box.
Okay. Yeah, let's see. So the first question here, how do we deal with the paradox of safety? Meaning other non-automated traffic participants might take more risk when they realize that automated vehicles become safer. Might this mask the fact that AVs get better? Yeah, this is an interesting question. This is kind of the joke that, you know, you put an automated vehicle in New York and everyone's going to be jaywalking everywhere because they know the automated vehicle is going to stop, right? And so we do have this kind of societal acceptance problem. It'll be curious to see how humans do it. I think the trick to this, though, is that the more that the automated vehicle drives like other humans, you probably just won't even be able to tell, or you won't know that that vehicle that you're driving next to is in fact an automated vehicle. And so if you're able to negotiate with other automated vehicles in the same way that you negotiate with other human drivers, essentially what you're doing is you're persisting essentially the same kind of transportation system that we have today in terms of how people drive. And then people may not take advantage of those vehicles quite so much. But it's still a fascinating question, and I'm sure we'll have lots of sociologists looking at how people respond to and behave here. So sorry, I don't have a better answer for you on that one. Next question is, how do AVs affect traffic capacity and mixed traffic? So this is a really good question, because one of the other important factors in consideration of picking values for those parameters is traffic flow, right? Is what should happen to the traffic capacity. If the AV is overly conservative and it maintains much longer following distances, it's going to have a negative impact on traffic capacity. That's why we pick, you know, a high speed for a certain road so that we can have a high throughput. And so picking the right values for AVs is really important to make sure that we maintain traffic capacity and don't have it drop by 50% just because we've introduced automated vehicles. In that sense, then again, you know, we're probably using the wrong values and might need to go back and look at those again. Let's see, so there's a comment about lane changing. Someone would like to mention that lane changing, a lane change, during lane changing, the braking capabilities of the vehicle get degraded due to the angle of wheels, and that should also be taken into account. Yeah, it's an excellent point. So there's the thing is, there's probably an infinite number of things that you could incorporate. Certainly things like coefficient of friction, perhaps the gradient or curvature of the road. Some vehicles know their own braking capabilities. And in this example here, right, as the wheels are turning, braking capability is also affected. And so there's a question, right, which again is a balance. Do I precisely calculate exactly to the centimeter or millimeter, you know, a particular safe distance or something like that by incorporating all these other different things? Or can I add a safety margin of 10, 20% to anything that I calculate? And then maybe now I don't have to have, you know, precise road gradient measurement capabilities or something like that. So again, it's always kind of a trade-off between how precise you want the calculations to be, which then, you know, means more sensors, more compute performance, things like that, and what you can make work just as well by just adding, say, a margin to account for the things that you're not calculating. Let's see, there was a question about the new research center that we're launching. Do we expect partnerships with other institutions? So this research center is meant to be an online collaboration area, so a virtual center, let's call it in that sense. We do fund research all around the world. The parameter derivation research that I presented earlier came from a research center that we have in China. We also are funding research in Europe and the US, of course, as well. And so that research center, the website, if you will, is a place to bring together all of the researchers from around the world that are doing work on RSS and those who are interested in doing new and more work on RSS. So it definitely will be a place for people to come together. No announcements with other specific institutions, but we'd welcome collaboration and partnership with any institution that's interested in collaborating with us on AV safety.
Okay, thank you very much, Zach. Is there perhaps one more question?
All right, so one more. Does the setting of these factors account for the behavior of the human driver that would take over in the outlier scenario? Interesting question. Yeah, we're not considering kind of the takeover or handover case in the standard that we're working on. We're considering kind of purely true automated driving, level 4 and level 5. So that is not a factor that we're accounting for, at least in the IEEE 2846 standard. And that is an important consideration, certainly. The ISO 4804 standard does talk about level 3 kinds of use cases where you might have a human takeover. And so I might refer you to that standard for the latest thinking from the industry about how to account for situations like that.
Okay.
All right, with that, I will thank you everyone for your time and for your excellent question. It's been an honor and pleasure to speak with you today, and I hope to someday still get to Greece someday. That was on my bucket list. So, so next year, hopefully we can reschedule and have it in Greece again. So thanks again.
We're thinking about that, Zach. We're thinking about that. Thank you very much. That was very interesting. And I think we can proceed with the next part of this plenary session, which is, it is about the awards, of course. We will start with the 2020 IEEE Transportation Technologies Award. I'm trying to see if the IEEE President Toshi Fukuda is online. I cannot see him actually. President Fukuda, if you are here, you can unmute yourself.
I see his name is over here, but he has been muted. Joe, can you unmute the speaker microphone?
I think the next one is the IEEE awards, right?
Evangelos, is the IEEE President Fukuda here?
That's what I'm trying to see. I think he's not. At least I cannot see him in the list. Okay. In any case, President Fukuda has sent me a message, and I will read to you his speech about the 2020 IEEE Transportation Technologies Award. So, next is the message from the President of IEEE. Good day, everyone. I'm Toshi Fukuda, the 2020 IEEE President. It is my honor to be able to participate in this celebration today and to represent the IEEE Board of Directors. I want to thank the organizers and other participants for their creativity and flexibility in successfully addressing the challenges of coordinating this online ceremony. It is more important than ever that we take opportunities to come together, albeit virtually, to recognize the accomplishments and contributions of our colleagues. By celebrating the pride and prestige of our professions, we also demonstrate how engineers, scientists, and technologists contribute to our global community and continue to build today's technologically advanced world. Today, we are presenting on one of IEEE's most prestigious technical field awards, the IEEE Transportation Technologies Award. This award is sponsored by several IEEE societies: the IEEE Industry Applications, Industrial Electronics, Intelligent Transportation Systems, Microwave Theory and Techniques, Power Electronics, Power and Energy, and the IEEE Vehicular Technology Societies. The award recognizes advances in technologies within the fields of interest to the IEEE as applied in transportation systems. This year, it is my pleasure to recognize IEEE Life Fellow Marcos Papageorgiou for his contributions to traffic flow modeling and operation. Marcos is a professor at the Technical University of Crete, located in Chania, Greece. The vehicular traffic flow modeling and control tools developed by Dr. Papageorgiou make travel safer, more efficient, help save energy, and reduce emissions by combating congestion problems on freeways and throughout urban centers. His local ramp metering algorithm, Alinea, which was developed in 1987, is recognized as a milestone in the field and is used around the world. In addition, the macroscopic simulation software MetaNet that he developed in 1989 for freeway networks is still one of the most widely used traffic flow tools. He introduced the concept of feedback in driver information and route guider systems and contributed to the deployment of large-scale implementation of travel time displays in Paris, France, involving approximately 450 vehicle management systems. Developed in 2005, his coordinated ramp metering algorithm HERO is widely considered the most advanced and efficient approach in this area. Marcos is a pioneer in the macroscopic modeling of traffic flow and the validation of such models. His work on this topic has strongly influenced subsequent developments and continues to be widely cited. On behalf of the IEEE Board of Directors, please join me in recognizing IEEE Life Fellow Marcos Papageorgiou, recipient of the 2020 IEEE Transportation Technologies Award. Professor Papageorgiou, congratulations one more. The floor is yours.
Thank you very much, Evangelos. And many thanks also to Professor Fukuda for his kind words. It is my special pleasure and honor to receive this great award. Great by the institution that presents it, which is IEEE, but also great by the list of past recipients. I would like to deeply thank my nominator, Professor Petros Ioannou, who is around, I'm glad for that, and who is himself a holder of the same award. I would like also to deeply thank the board of our society, of IEEE ITSS, in particular Professor Miguel Angel Sotelo and Professor Cristina Olaveri Monreal for their leadership and support in this matter. I have been active in the field of transportation dynamics and control since my PhD time, well before the appearance of the term ITS, Intelligent Transportation Systems. Nevertheless, a lot of intelligence was available even before, at that time, and a lot of progress has been made during all these years with the valuable contributions of many colleagues from various disciplines, and I hope that I could also contribute to these advancements to some extent. Please allow me at this point to cite some verses from a poem by the great German poet Bertolt Brecht. Young Alexander conquered India. He alone. Caesar bet the Gauls. Was there not even a cook in his army? I guess you get the meaning. We are praising big names in history, but they should have done nothing, but they would have done nothing without the hard work of many others. And it is similar in science. I am receiving today this prestigious award for work conducted with many undergraduate and graduate students, collaborators, and colleagues. And I would like to thank them all, as a big part of this award is actually theirs. Last not least, I would like to thank my family, my wife in particular, for standing by me over the years. Thank you all. We are a great society.
Thank you, Professor Papageorgiou. Thank you and congratulations once again. Then Weibin, I think we can proceed with the IEEE ITSS awards.
Yes, I'd like to ask Chinzhao to lead that award ceremony here by the society.
So can you see my screen?
Yes.
Yep. Okay, great. Hello, everyone. My name is Chunzhao Guo, and I'm VP Membership Activities of ITS Society. Here, we'd like to present the 2020 IEEE ITSS Awards. And this year, we had quite a number of high-quality applications from all over the world for the following awards, including ITS Outstanding Research Award, ITS Outstanding Application Award, ITS Institution Leader Award, ITS Young Researcher Engineer Award, ITSS Best Dissertation Award, and the ITSS Lifetime Achievement Award. And the competition was quite competitive. The first award we will announce is the Outstanding Research Award, which is for significant contributions to research in ITS-related fields. And this award goes to Professor Kazuya Takeda of Nagoya University for his contributions to data-centric driving behavior modeling. Kazuya is a professor and the vice president of Nagoya University in charge of information system and the information-related strategies. He has been working in the field of signal processing technology research, in particular understanding human behavior through data-centric approaches. He's currently highly active in the application of signal processing and machine learning technologies to the field of intelligent transportation system. Some of his contributions include building and sharing the driving signal corpora and leading the community. Driver individuality research, such as the spectral analysis of driving behavior signals and the stochastic modeling of car behavior with machine learning. Professor Takeda, if you are there, would you please say something to the audience?
Thank you very much, Go-san. This is greatest honor and pleasure of me, of course. And I know this is, of course, not the award only for me, but the award for all of my outstanding colleagues and students. So I like to thank all of them for pushing me here. Not because of this awarding, I'm proud of being a part of this society, because ITS, Intelligent Transportation System, is becoming one of the most dynamic elements of our daily life, which will change the future society, making it a safer, more efficient, and more comfortable. So I hope my research has contributed somehow to this big movement. Thank you very much again.
Thank you, Professor Takeda. And the next award is Outstanding Application Award, which will be presented by Ling Xi. Ling Xi, are you there?
Yes, I am. I'm here. Yeah.
Okay.
Okay. So next, so I'm pleased to introduce next awardee. So Mr. Matthias Schwartz from Visteon Electronics, for his contributions to the development and deployment of ADAS and autonomous driving technologies. So in his nearly 30 years involvement in ADAS and autonomous driving, Mr. Schwartz has contributed significantly to the large-scale market introduction of ADAS features and developing autonomous driving from a scientist's dream into a technology that is now not too far away from market introduction. So his main contributions include the Prevent project that leverages the market introduction of active safety systems in Europe. These systems are meanwhile either standard equipment in European passenger vehicles or prerequisite for a 5-star rating in European NCAP. Also, the first platooning system tested and demonstrated on public roads and test track in Europe, and the prototype's 3D mapping and a predictive cruise control system implemented as a production feature for all long-haul trucks of Mercedes-Benz, and deployed as predictive powertrain control on the 2nd generation Mercedes-Benz Actros trucks in 2014. And a modular and scalable hardware and software platform for environmental perception ADAS and autonomous driving. So Mr. Schwartz, if you are here, please say some words. Thank you.
Hello, yes, I'm here. Yeah,
Great.
Thank you very much for the kind introduction. And yeah, thank you very much to everybody. Yeah, still I'm lacking a little bit words, because yes, I have been active in the ADAS and autonomous driving field for a very long time, and yes, I have achieved something in these more than 30 years. But yeah, getting this award is nevertheless something very special for me, because yeah, it shows that what I've done is recognized on the one hand side, and on the other hand side, it shows that what I've done is, yeah, was right. So yeah, this award makes me, this extremely prestigious award makes me really proud. And again, thank you very much to everybody who has suggested me, who has supported to me. I feel really honored. Thank you.
Thank you. Congratulations again. Thank you.
Thank you. The next award is the institutional lead, which will be presented by Petros. Petros, please go ahead.
Yes, thank you. It is my pleasure to deliver the award, or to announce the award of IEEE ITS Institutional Lead Award to the Burns College of Engineering Center for Environmental Research and Technology, with the acronym CECERT, whose director is Matthew Parth of the University of California at Riverside. CERT has been, is a collaborative research center that involves the government, industry, and academia to develop and assess environmental technologies to improve transportation, air quality, and energy efficiency. CECERT has been and continues to be a leader in education and research on transportation technologies with a strong contribution to solving societal environmental issues. Some of the main contributions of the centers is leadership in research on eco routing navigation systems, dynamic eco driving systems, and eco signal systems. And in addition to all these research contributions and visibility in the area, I would say is one of the, if not the only one, big center in this area of research. The director, Matthew Parth, has been very active with the ITS Society. He serves as president, and he continues to be active as part of the executive committee and the board. So the society appreciates these contributions too. So with that, I will congratulate Matthew Parth and his center for the award and leadership in this area.
Great. Thank you very much, Petros, for the introduction, and thank you to the ITS Society. This is truly an honor to receive this institutional award. And again, this isn't so much an award for a single person, it's an award for a research center that's really focused in on transportation, energy needs, and of course, other environmental topics such as emissions and air quality. We got our center established nearly 30 years ago with a major focus on the environment. And then coming into this as electrical and computer engineers, you know, intelligent transportation systems can and do play a very important role in terms of solving those environmental problems. So it's not just about electrifying all the vehicles, but it's also studying things such as shared mobility, and then how can we leverage connected and automation to really focus on the environmental issues. We just heard a great keynote focused on safety. You know, in a lot of ways, the environment's related to safety too, right? We have air to breathe and energy resources and things like that. So from the institutional point of view, it's a large group of people that come from different research areas. But on transportation, I really want to thank a lot of the different research faculty and faculty members that make this up, in particular, Dr. Kanuk Bodibun-Somsin, Dr. Guyan Wu, Dr. Peng Hao, and Dr. Shams Tanvir. They've done quite a bit of work in this research area. And of course, many of the graduate students and undergraduates that are involved. So again, on behalf of the entire Research Center, I want to thank the IEEE Intelligent Transportation System Society. This is truly an honor. Thank you very much.
The next award is the ITS Young Researcher and the Engineer Award, which will be presented by Brandon. Brandon?
Hi. The award, oh, yep, thanks. The award for the ITS Young Researcher Award goes to Professor Xiaosong Hu from Chongqing University for his contributions to electric vehicle battery management systems and electrified vehicle optimization in ITS. For those that aren't aware, the IEEE ITS Young Researcher Engineer Award recognizes early contributions and leadership in research and/or application in ITS-related fields. Professor Xiaosong Hu is the director of the Intelligent Electric Vehicles Lab in the Department of Automotive Engineering and the vice director of the Chongqing Automotive Collaborative Innovation Center. He's an active researcher in sustainable and intelligent mobility solutions, which are facilitating the shift to a green transportation future. Specifically, this award recognizes Dr. Hu's main contributions, which include the concept of a Li-ion battery model, usefulness for improved battery management, control and optimization for hybrid electric vehicles, and a predictive energy management strategies for connected electrified vehicles, which use dynamic traffic information and V2X communication for improved fuel economy. I'd like to welcome and congratulate Dr. Hu for his great work. And if he's here, I would appreciate if he could say a couple of words. Thank you.
Yes, first of all, I would like to thank the ITS Society for presenting this important award for me. It's my great honor and pleasure to receive it. This will definitely encourage me to do more innovative research on intelligent electrified vehicles. Thank you very much.
Thank you, Professor Hu. Our next award is the ITSS Best Dissertation Awards, which will be presented by Yisheng. Yisheng, are you there? So Yisheng told me he might have some problem in joining the meeting. So if he's not there, I will present this award for him. Okay. Each year we have the ITS Best Dissertation Award based on the quality of their dissertation. And the third prize of this year's Best Dissertation Award goes to Dr. Holger Benzoff. He graduated from Karlsruhe Institute of Technology, Germany, and he's with Bosch. And the title of his dissertation is Non-Holonomic Motion Planning for Automated Vehicles in Dense Scenarios. Holger, if you are there, please say something.
Hi, this is Holger speaking from Germany. I hope you can hear me. So first of all, a big thank you to the ITS Society for this great award, as well as for the 2 other paper awards that I've received during my PhD time. This clearly gave me a lot of motivation to deepen my research in the various automated driving topics. Also, I would like to thank Professor Zöllner, Director of the Technical Cognitive Systems Group at the FCI Karlsruhe, for the scientific supervision of my thesis. And last but not least, this work would not have been possible without the support of the Robert Bosch GmbH that provided me with the resources and a very inspiring environment. So thank you very much.
Thank you. The second prize goes to Dr. Shuo Feng. He graduated from Tsinghua University, China, and he's with the University of Michigan, Ann Arbor now. The title of his dissertation is Testing Scenarios Library Generation for Connected and Automated Vehicles. Sure, if you are there, would you like to say something?
Yes. Hello, everyone. Here is Shuo Feng. It is my great honor to receive this award. First, I would like to express my appreciation to the award committee for their recognition and encouragement to me. Second, please allow me to send my gratitude to my supervisor, Dr. Yi Zhang from Tsinghua University and Dr. Henry Liu from University of Michigan. This achievement could not be received without their guidance and support. I would also like to thank all the collaborators, especially Dr. Feng from Purdue University and Dr. Li Li from Tsinghua University. Their helpful suggestions have been important for this dissertation. Finally, I want to thank my parents, my beautiful wife, and my little baby for their unconditional love and endless support. Thank you. Thank you all.
Thank you, Dr. Feng. And the first prize goes to Dr. Naga Meir. She graduated from UC Berkeley and she's with UNECE now. The title of her dissertation is Smart Traffic Operation from Human-Driven Cars to Mixed Vehicle Autonomy. Dr. Meir, if you are there.
Hello, everyone. I hope that you're hearing me well. This is really exciting. I would like to thank the award committee for selecting me. It's really an honor to receive this award. I would also like to thank my advisor, Professor Roberta Horowitz, and all the faculty at Berkeley who helped me with this thesis for their support and guidance throughout my PhD years. Thank you, everyone.
Thank you. And note that all the awardees who received the Best Dissertation Awards will give presentations of their doctoral works at this year's IEEE conference. So please stay tuned. Okay, the last award is ITS Lifetime Achievement Award, which will be presented by our president, Wei Bin. Wei Bin, please go ahead.
My name is Wei Bin Zhang. I'm the president of IEEE ITS Society. It is my pleasure and honor to introduce the recipients of this year's IEEE ITS Society's Life Achievement Award, Professor Masayushi Tamisuka of the Department of Mechanical Engineering at University of California, Berkeley. The Life Achievement Award is the highest honor given by IEEE ITS Society to recognize contributions over the whole of a career. This year's award is given in recognition of Professor Tamisuka's vision, creativity, and enormous contributions to the field of intelligent sensing and control for automated driving. Professor Tamisuka received his bachelor and master degrees in mechanical engineering from Keio University in Japan, and his PhD degree in mechanical engineering from MIT. In 1974, he joined the faculty of Department of Mechanical Engineering at the University of California, Berkeley, where he holds the Cheryl and John Niao Jr. Distinguished Professorship Chair. He has served as Associate Dean and Executive Associate Dean of College Engineering at UC Berkeley since 2011. He served as Program Director of Dynamic System and Control Program of the Civil and Mechanical System Division of NSF from 2002 to 2004. Professor Tamisuka's research interests are optimal and adaptive control, digital control, motion control, and their applications to robotics and vehicles. What becomes the most relevant to this award is his contributions to early research in the United States on automated vehicle control theories and applications, the conceptual work of automated highway systems, and intelligent transportation system in general. Professor Tamisuka has been a founding member of California PASS program, the first ITS research program in the United States. His work on preview vehicle control, based on his finite preview optimal control theory, has established the foundation for PASS vehicle lateral control, which later has been cited and applied by many across the globe. His work has been extended from automobiles to trucks and rail vehicles, and human driver modeling and prediction, as well as situation awareness control systems for autonomous vehicles. He has published more than 850 papers in archived journals and referate conference proceedings. Many of these publications are in the field of ITS. While there are many aspects can be said about Professor Tamisuka's research achievements, his educational contributions are of equal superior quality. To date, he has mentored 125 PhD students to completion. Many of his former students are now working as leaders in academia and industry internationally. Professor Tamisuka is a Life Fellow of IEEE, an honorary member of ASME, and a Fellow of International Federation of Automatic Control and Society of Manufacturing Engineers. He has many honorary awards and has been elected by his peers to many important posts that time does not permit a full listing of each. Before I give the floor to Tommy, on behalf of ITS Society and many colleagues who are in the audience, I would like to extend my congratulations to Tommy for receiving this prestigious award. To add a personal note, I have the honor and privilege working closely with Professor Tamisuka for the majority of my 30+ years at UC Berkeley. I have been benefited tremendously from his advice and help. Tommy has consistently led our thinking of a wide range of issues related to automated vehicle control and emerging technologies. As a colleague, I would like to extend my congratulations on this well-deserved award. This is a wonderful acknowledgement of your lifelong work. Let's welcome Professor Tamisuka.
Okay, thank you very much, Wei Bing, for wonderful introduction. And you highlighted important part already, so probably I don't have to do any presentation, but I'm truly honored by this Lifetime Achievement Award from IEEE ITS Society, and I thank for the IEEE group of people who nominated me and also supported my nomination, and also the ITSS Award Selection Committee for selecting me for this award. I think that I prepared actually some presentation slide. I noticed that nobody used presentation file, but I prepared one which duplicating a lot with what Wei Bing already said. But let me try whether I can show my presentation. Oops, yeah. Okay, so I call the presentation ITS and I in absence of not any better title. And actually, I've been in this field quite some time, and amazingly enough, my first involvement in this what we call ITS happened when I was a student at MIT. I was there from 1970 to 73, and the first project that I was asked to do was normal and emergency control of single vehicles by fixed reference sample data control. And it was part of the so-called personal rapid transit. And around that time, the people at MIT were interested in this personal rapid transit. And it was something called fixed, for each vehicle is controlled by itself. No platooning and so forth. So the idea was set up a post along a guideway, and each post was generating a signal, essentially cyclic signal going back and forth. And the idea is if the vehicle is at the post at the right moment, the vehicle receives 0 signals. By changing the frequency for fixed distance between 2 posts, by changing the frequency of this signal, they can adjust the speed to any value they deem appropriate. So that's how this idea worked. And that was my first year work at MIT. And then the second year, I switched subject to something called optimal finite preview problem. I'm introducing this because that set some foundation for my work in past organization. So in this preview problem, I worked on some formulated from optimal control point of view, how we can best utilize the future signals available to the controller. So for example, if we are to track this type of trajectory, and t is the present time, I divided the future into 2 parts. One is deterministic future, which is known to the controller, and the rest is so-called statistical probabilistic future that I really don't know. Okay, so from stochastic control point of view, I figured out how I can best utilize this deterministic knowledge as well as some statistical information. Okay, so preview and predict, that was a combination. That I did for my PhD, and I left MIT in 1973. Okay, and then I joined UC Berkeley in 1974, and PASS was founded in 1986. PASS at that time stood for Program on Advanced Technology for the highway, because I just put this name because PASS now, still we use PASS, but now it means something different. But this is what I meant by PASS when I joined. And PASS was established to California vision of highway systems, and automated highway system was a big part. And advanced technology included dynamic systems and control. So unlike other transportation projects, there are quite a few participation from EECS and ME faculty, and especially control faculty, and people like Charlie Dezoa, Pravin Varaya, who came up with some nice AHS architecture, and Carl Hedrick and myself. Actually, the Carl joined the year when the PASS really started doing research work. So, either are you seeing something disturbing the screen? I cannot see how I can get rid of this, but bring this somewhere else. Okay. So Carl joined in 1988, and he and I are both do so-called vehicle level regulation control. And since I did some work on the longitudinal direction control when I was an MIT student, I was more interested in looking into lateral dynamics, and Carl did longitudinal control. So we were in the orthogonal direction, but we had a great time together. And this is the PASS lateral control scheme. And we have a bunch of sensors on the vehicle side. But one important unique feature of the PASS lateral control scheme was the magnet markers buried in the center of the vehicle lane. And magnetometer on the vehicle side sense where the vehicle is relative to this magnet. And this magnet idea actually came from Wei Bin, and we utilized his technology. And as he said, we interacted each other quite a bit since I joined the PASS research group. Okay, so magnet at the beginning looks like this, and measuring magnetic field both in the horizontal and vertical direction by the magnetometers, we could have a very robust measurement of where the vehicle is relative to the magnet. So Wei Bin's idea became his patent, and we had some unique technology there. In terms of control, I was applying optimal control. So the idea was how we can minimize tracking error, ride quality, and sensing effort by quadratic cost. But one twist was it was frequency dependent, the cost. So we called frequency shaped optimal control, FSLQ, linear quadratic control. And more than that, we minimize the accounting for previewed future load curvature from T to TLA. Such information may be actually coded into the polarity sequence of magnet if we like. There are several other ways of doing, but preview was the key idea. Instead of driver looking down at the magnet, driver always sees ahead. So we actually bring that idea to control. And this is where my PhD dissertation made some good use. So preview control I did in 1973 found some good application there. And the control included the state feedback control and how we can make use of the curvature information in the future. So that's preview control. And in fact, the Professor Wei Peng, now at Michigan, was my first student on this PASS project. And he was convinced that the preview is the right approach. And that became his PhD dissertation, and we published a paper in the ASME journal. We could have actually preview information not just by the by having coded information. But if we have magnetometer on front end and rear end of the vehicle, we could extrapolate and we could have the future target point by or any error from the middle lane by this extrapolation idea. So I think that we used this scheme quite extensively as path activity, lateral control activity developed in our group. So there are lots of algorithms proposed. The first proposed algorithm was frequency shaped linear quadratic control with preview. Then as the sliding mode control was introduced, this one really didn't require to do the front rear magnetometer scheme, because having the magnetometer at the front, it's always relatively ahead of the center of gravity. So sliding mode control, high gain control was achieved. Then some linkage-based control idea, loop shaping control idea, they were introduced. And the past highlight was the demo 97 in San Diego. And I think we used loop shaping controller in the AHS demo. So this is one picture, one photo from the AHS demo. The path is very known for the platooning work. So this is 8-car platoon doing automated control in both longitudinal and lateral direction. 2 lanes, each lane were installed magnet, included the lane following and lane change. And in addition to this lane following, we have done quite a bit of work, including lane change and fault tolerant control, as well as fault management, etc., etc. And I introduced several interesting, unique work that we have done. And we are always wondering what will happen if the tire blows up while the car is under control, automated highway systems, because that happens not so every day, but that happens and we find some tire remnant on the freeway. So the Patwald tire design a mechanism to suck air almost in 0.5 seconds from tire, and we did some controlled flat tire experiment, and we found that if we can have some emergency controller which sends the tire deflating and send some kick, we can bring the control, the vehicle to the stopping very safely. We did experiment and actually extended work to the heavy vehicle. So Freightliner tractor we used, and we did both theory development and experiment for this type of the heavy truck trailer. And now people are talking a lot about autonomous vehicles, and we are utilizing our knowledge from the past days in the design of vehicle lateral control for autonomous driving. Actually, more than lateral control. We are aiming level 4, level 5 through automation. And certainly it is more than just the control. We have detection, tracking, prediction, behavior modeling, human driver, environment modeling, decision-making, motion planning, and so forth. So we have a standard vehicle control loop, but on the top of that, we have planning, prediction, decision-making, and so forth. The one emphasis that we have in my group is how we may integrate model-based control, which has got theoretical guarantee for stability, feasibility, and safety, and we can incorporate prior knowledge on dynamic model, HD map, and so forth. Model-based control and machine learning. The machine learning has got some nice advantage, and many people actually work on this machine learning aspect. And as a control group, we are working hard how we can blend those two seemingly different approach and take synergy and make a very nice autonomous vehicle systems. I acknowledge the work by past and current collaborators, colleagues, and graduate students. Like Wavin said, I've graduated 125 or so PhD students. That also explains why I have so many papers published. And here in this talk, most of the work was done by my bright graduate student. The research was sponsored by Caltrans, California Department of Transportation. Industrial sponsors Berkeley Deep Drive in these days. I didn't list each of the industrial sponsor or student because if I start listing, I will miss some. Thank you very much again. This is truly an honor to receive this award. Thank you.
Thank you, Tommy. Again, congratulations. Really well-deserved award for you. We're very, very happy for you. I think that the ceremony is about to close, but I want to make an announcement before I hand over to Kunjo. The IEEE Symposium is going to start within about 23 minutes, 8:30. I wish you can all join that IEEE ITE Symposium a little later. Kunjo?
Yep, thank you. And let's congratulate all the awardees again and for their great contributions to the society. And here I also encourage all of you from the audience to apply for our prestigious ITS awards in the future years. Thank you very much. Have a good day.
Yeah, that ends today's award ceremony. Thank you.
Thank you.